Hello everyone, my name is Tony and welcome to Kevin and my presentation about optimal path planning algorithms for collaborative robots. This is a comparative study where we simulated and evaluated different path planning methods that gives us some insight to how each of them could impact robotic operations in warehouse environments and which one could be the best for different settings. Let's dive into the details. Warehouses are becoming increasingly complex as automation takes center stage. In such environments, mobile robots must navigate intricate layouts, avoid collisions, and collaborate effectively to ensure the highest throughput. The challenge is balancing these demands while maintaining safety and efficiency. Our study aims to address these challenges using machine learning and path planning algorithms. We explored three key goals: real-time navigation in dynamic and sometimes unpredictable environments, avoid collisions without compromising efficiency, and optimizing resource use while ensuring task completion. The motivation for our work is simple. Different problems requires different solutions. There's no one-size-fits-all when it comes to path planning, and we aim to provide a look into various methods' strengths and weaknesses so that you can choose the best option for your specific needs. Now, let's discuss the experimental setup and algorithms we evaluated. We compared three methods: one-step value iteration, window hierarchical cooperative A-star, and conflict-based search. To test these algorithms, we built a grid world with four robots operating over 1 hour in two scenarios, one with four shelves and the other with five. We measured performance using three criteria: number of tasks completed, this quantifies overall efficiency; computational cost ratio, to assess the algorithm's feasibility in real-time settings. For example, if a robot uses tenth of a second to compute a path that takes 1 second to complete, the ratio is 10%. And energy efficiency, which reflects the average travel distance compared to its theoretical optimal. These three critical metrics allows us to fairly compare how each algorithm performs. Let's take a closer look at the first algorithm, one-step value iteration. This method uses value functions to iteratively optimize decisions. By balancing immediate rewards and future benefits, it adapts to dynamic grids and task requirements. Its key strengths include producing globally optimal solutions for static environments and handling complex grid with ease. However, the algorithm's computational cost rises significantly in dynamic or large-scale setups, making it challenging to use in real-time applications. The results were promising. One-step value iteration stood out for its ability to foresee potential collisions and takes preemptive actions. The capability not only improved energy efficiency, but also led to higher task completion rates compared to the other algorithms. However, the trade-off was clear. The high computational cost makes it less viable for scenarios that require real-time adaptability. The second algorithm we tested was Windowed Hierarchical Cooperative A-star, or WHC A-star. It plans paths within a fixed time window and uses reservation tables to avoid conflicts. By combining local and global optimizations, it balances adaptability and computational feasibility. It handles real-time changes effectively without using excessive computational resources. However, its fixed window size limits long-term foresight, often leading to suboptimal solutions for longer planning horizons. Our results showed that WHCA star excels in real-time scenarios with the lowest ratio of computational cost of less than 0.3%. This allows it to adapt quickly, making it suitable for dynamic environments. However, its limited foresight means it can't always optimize task completion rates, particularly in more complex layouts or when tasks require longer planning horizons. Finally, conflict-based search, or CBS. This algorithm allows each robot to plan independently at a low level, and at a higher level, it iteratively detects and resolves path conflicts. CBS has superior conflict resolution. This ensures collision-free paths. It is also quite flexible, easily allows scaling to large robot teams without compromising individual goals. That said, CBS can be computationally intensive, especially in complex environments. It also tends to be slower than WHCA star on large grids due to its iterative conflict resolution process. CBS performed exceptionally well in scenarios involving multi-agent setups. Its strength lies in its ability to ensure collision-free paths while maintaining task efficiency. However, when tested on larger grids, its processing speed lagged behind WHCA star. This slower performance stems from the algorithm's step-by-step conflict resolution process, which can become cumbersome as grid size and task complexities grow.
As a comparative study, we make a comparison of these three algorithms based on experiments conducted in the two warehouse settings. The results are summarized in this table. First, we observe that all three algorithms effectively avoid collisions throughout the entire simulation process. However, there are notable differences in their performance criteria. One-step value iteration stands out with the highest energy efficiency and task completion rate, making it highly effective for achieving task capacity of multiple agents. However, this comes with a trade-off. Its computational cost is significantly higher compared to the other two algorithms. On the other hand, WHCA star and CBS demonstrate much lower computational cost while still maintaining relatively high energy efficiency and task completion rates. WHCA star, in particular, have computational costs that are almost negligible, making it a highly practical choice for real-time applications. These findings highlight the trade-off between computational cost and performance, helping to guide the selection of algorithms based on specific use case in warehouse setting. Let's look at how these algorithms behave in collision avoidance, which we believe is a key factor influencing the task completion rates and energy efficiency. One-step value iteration is proactive in handling collisions. It can foresee potential conflicts and take early actions to avoid them. As shown in the animation, some agents proactively move through the central area to avoid conflicts. As a result, agents tend to scatter across the environment, which reduces the conflict rates. In contrast, WHCA star and CBS exhibit similar reactive behaviors. They are unable to foresee one collision unless it is about to happen, at which point they take urgent actions to avoid it. As shown in the animation, agents rarely enter the central zone and take urgent actions when collision is about to happen. As a result, agents tend to gather, which increases the conflict rates. As for conclusions, our findings highlight two key insights. First, in terms of foreseeability of collisions, one-step value iteration outperforms WHCA star and CBS in foreseeing potential collisions and preventing agents from gathering. This foresight increases energy efficiency and task completion rates, but results in high computational cost. Second, regarding suitability for applications, one-step value iteration is best suited for environments where energy efficiency and task completion are prioritized over computational cost. WHCA star and CBS are more appropriate for scenarios demanding real-time responsiveness and low computational cost, even if it sacrifices some task efficiency.